Hello everyone, myself Mugilan from K.S.Rangasamy College of Technology. In this video, we are going to discuss about image restoration process. So, first of all, need to know about what is image restoration. So, the restoration uh, is to restore the images that has been degraded by means of noise and all. So first of all, identify the degradation process and to attempt to reverse it. And it is very similar to image enhancement, but more specific to the objective. So next, noise and images. So here, the source of noise in digital images arises during image acquisition, that is sampling and quantization, that is digitization and transmission. So the imaging sensors can be affected by ambient conditions. So the interference can also be added to an image during transmission. So these kinds of noises will degrade the image. So the noise model. So the noise model, the expression for noise model is given here. So g of xy is a image equal to f of x comma y plus eta of x comma y. So this f of x comma y is the original image pixel and eta of x comma y is the noise term, and the resultant noisy pixel is g of x comma y. This is the expression in terms. So if we can estimate the noise model, we can figure out how to restore the image. So here the different types of noises are given. So the Gaussian noise, the Rayleigh noise, Erlang, exponential, uniform, impulse. So generally the impulse noise can be known as salt and pepper noise. So most commonly noise model is Gaussian noise, and the Erlang can be represented by Goma noise. So these are the noise models. So here the image shown here is degradation and restoration process. So the f of x comma y is the image, the degradation function is h, and the noise is eta of x comma y. This noise is added with the original image, the g of x y. So again the restoration process, the noise are removed. So after removing, that can be called as f cap of x comma y. So blurred and additive. So main objective of this is removal of noises, that is remove degradations. So degradation function is a linear and shift invariant, and the degradation model in spatial domain and frequency domain, where in the spatial domain small g of x comma y equal to h of x comma y into f of x comma y plus eta of x comma y. It is a nice variant. In frequency domain, it is capital G of u comma v equal to h of u comma v into f of u comma v plus capital N of u comma v. So the nonlinear spatially varying degradation functions common, but much harder to handle. So the noise model has random variables are shown here. The noise value is determined by the PDF, that is probability density function, and the common assumptions made for noise probability density function is correlated to image by itself, and it is independent of spatial coordinate, or it is periodic one. So the example of image without noise is given here, and the different noises are added into that original image The types of noises are Gaussian, uniform, and impulse noise. So the impulse noise is nothing but the salt and pepper noise. So the Gaussian, the histogram of Gaussian uniform noises are given in the graph. And next, the estimating of probability density functions. One of the possibility is fit PDF parameters to histogram to uniform the region. It's one of the possible method. The Gaussian noise is given here. The probability for image values PS of zi, and the estimated for histogram is estimated mean and estimated variance is given here. The uniform patch of the image is given here, and the histogram diagram for the uniform patch is given here. In this region, the mostly belongs to this region. And the image restoration, different process, or the modeling of image restoration and degradation process. Restoration under noise only, estimating the degradation function, inverse filtering, Wiener filtering, constraint least square filtering, Richardson Lucky non-blind deconvolution. These are some of the image restoration process available. And filtering to remove noise. So you can use spatial filters of different kinds of remove different kinds of noises. Here that arithmetic mean filter is used. Arithmetic filtering mean can be calculated by using the given formula, that is f cap of x comma y equal to 1 by m into n and summation of g comma t, where s of t is belongs to s x y. Is implemented as a simple smoothing filter plus the image. So this is one of the filtering method of for removing the noise. And other means of filters are geometric mean filter, harmonic mean, and control harmonic mean. Where in the geometric mean, the formula used is f cap of x comma y equal to uh, pi of g of x comma t, the whole of 1 by m into n, and it achieves the similar smoothing to the arithmetic mean, but it tends to lose less image detail. And the next one is the harmonic mean. In harmonic mean, f cap of x comma y equal to mn divided by summation of 1 by g into s comma t. It works well for salt and pepper noises but fails for pepper noise. Also does well for other kinds of noise such as Gaussian noise. This harmonic filter. And then contra harmonic mean, there is f cap of x comma y equal to summation of g of s comma t power q plus 1 divided by summation g of s comma t power q. So the q is the order of the filter, and the positive values of q eliminate pepper noise and negative values of q eliminate salt noise. So it cannot eliminate both simultaneously. This is the contra harmonic mean. And the figure shown is the different noise removal examples. So the original image of a PCB board is given, and the corrected by Gaussian noise is given in this picture. And the arithmetic fin filter, that is 3x3 arithmetic fin filter image, and geometric mean filter, less blurring than AMF arithmetic mean filter. The image is more sharper than compared. So so far in this video we have discussed about the image restoration and degradation processes, how the noise is eliminated by means of using different filters. That's all about this video. Thank you everyone.